Hi, my name is Leah Carneiro, and I'm going to be presenting my work from the 2023 AAS GN&C conference titled Spacecraft Simulation Software Implementation of General Prescribed Motion Dynamics of Two Connected Rigid Bodies. And I'd like to thank all of my co-authors for their support in this work. So this paper is motivated by new, ambitious, innovative spacecraft that are consisting of multiple connected rigid bodies that are attached to our central rigid spacecraft hub. Some examples here are solar arrays, robotic arms such as the Canada arm seen here, gimbal thrusters, and communication antennas. And these multi-body systems, the dynamics of these bodies are inherently coupled, and they're challenging to implement in software because the motion of all of these rigid bodies are impacting the motion of all of the other bodies in the system. So the main goal of this work is first to investigate the effects of the motion between a rigid spacecraft hub and a connected secondary rigid body. And this rigid body is unique in that its motion is prescribed. I'm going to be talking about what that means in the next slide, and it's also free to translate and rotate. So it has 6 degrees of freedom. And the second goal here is to develop a way to simulate the derived dynamics of the system in a general and modular way in software so that we can simulate different types of multi-body spacecraft systems. So what is prescribed motion? It involves the explicit definition of a rigid body's states over a given period of time. So we're essentially assuming that we know the states of this rigid body over the entire period of motion. And consequently, this does not involve numerical integration for the equations of motion for this prescribed body. And this is because we have a one-way coupling between the spacecraft hub motion and the other rigid bodies in the system and the motion of our prescribed body. So here we're essentially assuming that when our prescribed body is moving, it does have a coupling between the motion of the other body. So it is affecting the dynamics of all of the other bodies, but when the other bodies in the system move, this doesn't affect the motion of our prescribed body. So some classic examples here are stepper motors, articulable solar arrays, actuated platforms, gimbaled thrusters, servo sensors, and any sort of robotic manipulators. And there's just a wide variety of applications for this prescribed motion work that we're investigating here. So for our dynamics derivation, we consider 4 frames. The inertial frame is used as our reference frame for developing the equations of motion of our spacecraft hub. We have our spacecraft hub here in gray. The B frame is denoted as the hub body frame, and our center of mass of our hub is denoted this BC. And we are denoting our prescribed body in purple here, and it's the body frame that's tracking the position and attitude here is the F frame. And then we also have this intermediate mount frame M. It's attached to our spacecraft hub. It is body fixed to the hub, and it's essentially serving as a point of reference that we are defining our prescribed body states with respect to our spacecraft hub. So with these 4 frames, we're going to go through a brief overview of our translational equations of motion and then our rotational equations of motion. So first, for our translational equations of motion, we start from Newton's second law for the acceleration of the center of mass of our system with respect to the inertial frame here. So this C vector here is denoted as the vector from our B frame origin to the center of mass of our system. So we essentially need to find our acceleration here, our inertial acceleration of this C vector. So anytime we see a dot in this derivation, it denotes an inertial time derivative. However, when we see a prime, this denotes a B frame relative time derivative here. So when we substitute this expression C double dot back into our Newton's second law, we still need to find what the C vector is, our C prime, and our C double prime is. So we can simply define our C by taking the contributions from the hub and our prescribed body. We are calling this P, so we have a subscript P here, and then we divide by our total system mass. And then we essentially take our B frame time derivative here, and we can note that because these are rigid bodies, any time derivative taken in the respective body frame of our center of mass location of this body is always going to be 0 with respect to the origin of our respective frame. So then we can take our second B frame derivative, and we have these quantities. We also can define both of these vectors here. I'm leaving out quite a bit of math, but then when we substitute all of these quantities back in, we come to our translational equations of motion. And we can do something very similar for our rotational equations of motion, except we're starting from Euler's equation. But first we define our angular momentum about point B for our spacecraft system, and we can add the contributions from the hub and our prescribed body here. So we have both of these expressions, and then we can combine these terms here to call our total spacecraft inertia about point B here. So we then come to a compact expression for our angular momentum of our spacecraft about point B. And then we can essentially take our inertial time derivative here to get to our rotational equations of motion. And leaving out a great bit of math here, we essentially come to our rotational equations of motion for our spacecraft hub here. So now that we have our equations of motion, we want to implement them in software. So we chose the Basilisk astrodynamics software for implementing these equations of motion. And the reason why we're doing this is because Basilisk is very modular, and it utilizes a back substitution method to essentially append different rigid bodies to our spacecraft hub in a very modular way so that we can efficiently integrate our equations of motion of our hub by essentially taking all of the contributions of each rigid body that's connected to our spacecraft hub. So if we rearrange our translational and rotational equations of motion into this form shown here, we will see that our ABCD system mass matrix is going to be all zeros for this problem. On our right-hand side, this V-trans and this V-rot, we essentially have all of our contributions from our prescribed body. So we can directly see here that our prescribed body is that the states of our prescribed body are directly impacting our hub's accelerations. However, because we have these 0 ABCD matrices in our system mass matrix, the motion we have a one-way coupling here, and the motion of our hub is not impacting the motion of our prescribed body. So now that we have these equations of motion, we specifically wanted to create 3 different modules in Basilisk. The first module is our prescribed motion state effector dynamics module. And that's the module that's essentially holding all of our equations of motion that we derived here. And then we also need different profilers to be written to actually prescribe what these prescribed states are. So we have a rotational profiler module, and we also have a translational module. So Our simulation setup, we set up our spacecraft into a circular orbit about the Earth, and it's the angular velocity of our B frame is initially 0, and we also have our hub attitude aligned inertially to begin. And we also have our initial prescribed body states. There's quite a few vectors here that are all zeros, but essentially our prescribed body is not translating or rotating at the start of either of these maneuvers. We essentially also need to define our reference states for the rotational and our translational maneuver here. So we, for our rotational maneuver, we want to move through 30 degrees about our first mount frame axis. And then we also, our rotational axis here, it's also the first F frame, like body axis. And then we also define a maximum angular acceleration for our rotational maneuver. And then we essentially do the same thing for our translational maneuver, where we have, we want our body to move 1/2 meter along this translational axis. This axis is defined in the mount frame. And then we also define a maximum like translational acceleration here. And so essentially what each of these maneuvers is doing is we're applying a constant positive acceleration for the first half of the maneuver and a constant negative acceleration for the second half of the maneuver, so that we arrive to our reference state with 0 residual angular velocity or linear velocity. So for our rotational profiler, we're given our initial attitude, our reference attitude as a principal rotation vector, and a maximum angular acceleration set by the user. And with this information, we can define our relative PRV for this maneuver. So essentially, this phi ref is the angle that we need to move through to converge to our desired reference attitude. So with this information, we can define our required maneuver time and then also our switch time that we are changing from a constant positive acceleration to a constant negative. So for our first segment, we have the positive acceleration here described by these equations. We can see that our angular velocity is expected to be linear, and then our angular position is going to be parabolic as a function of time. And then for our segment 2, we essentially have the same thing, except we have a negative acceleration here. So now for our rotational motion results, we have our prescribed angular acceleration exactly as we expect for our maneuver. And then we also have our prescribed angular velocity, which is linear, and we reach a 0 state of angular velocity at the end of our maneuver. We can also see that this our hub is responding accordingly by essentially compensating for this prescribed rotation, and our hub is rotating oppositely to keep our conservation of angular momentum here. And then we also have our prescribed angle phi, and we can see we are going smoothly from 0 to our reference 30 degrees, parabolically upwards, concave upwards for the first half, and then concave down for the second half. And our hub attitude is responding accordingly to compensate as well here. So in order to verify that our implemented dynamics are accurate, we're essentially checking a few conservation quantities here. We're checking our orbital angular momentum, our rotational angular momentum, our orbital energy, and our rotational energy. And we're expecting when we take the, when we subtract our current value from our initial value, we're expecting to see a very like machine precision like plot here. So we can see we're using an RK4 integrator. So we have some sort of like random walk happening here. Our axes are 10 to the negative 15. So these are looking just as we expect for our equations of motion here. And then we also have our change in our orbital energy and our rotational energy. So we aren't expecting our rotational energy to be conserved because we're essentially adding energy into our system when we're accelerating positively, and then we're removing energy when we are decelerating. So we aren't expecting that to be conserved. However, we are expecting our orbital energy to be conserved. Here, our axes are not on the order of 10 to the negative 15 or around there. And we're sort of attributing this to the fact that our prescribed states are held constant over our RK4 integration substeps. So we are having some sort of inaccuracies here because we aren't varying our prescribed states over that smaller time step. But generally, these results are what we are expecting, and they are like concluding that our derivation is accurate. So then we did the same thing for our translational profiler. We're given our initial position, our reference position, our relative position vector. And then we again have our positive acceleration segment 1 and then our negative acceleration segment 2. And then again, here we are translating about an axis that's sort of an intermediate axis. It's not like our first axis or second axis or any of that. So we do have a zero acceleration for our second, our double prime here. But then our prescribed velocity is linear in our first and third components, which is exactly what we're expecting here, and 0 in our second component. And then our position is seen here to converge to our reference vector components here in a parabolic way. And then we also see here that because this is a translational maneuver, we're not expecting our hub attitude to shift or our hub angular velocity to shift, and our axes are on the order of 10 to the negative 15, 10 to the negative 14. So this is as accurate as we need to see here, so we can essentially confirm that these results are as we expect for these equations of motion that we have derived. And then we also are checking our conservation quantities again. Here we have our orbital angular momentum and our rotational angular momentum. Our axes are not as looking as nice as before, but we do have them to be 10 to the negative 10. And we are also attributing these effects to holding our prescribed states constant over the RK4 time step. And then we also have our change in orbital energy, which is looking great. Our axis is 10 to the negative 13. And again, we're not expecting our rotational energy to be conserved either, because we are accelerating, so we are adding energy into our system, and then we are removing energy when we are decelerating. So we still have some work to be done here to really verify that our dynamics are implemented correctly, and we really would like to, in the future, we would like to hold our prescribed states not constant over our RK4 time steps, so that we can really see that these quantities are conserved as we are expecting. But for now, our preliminary analysis is showing that our dynamics derivation is looking to be correct. So thank you so much for watching. And if you have any questions, please feel free to email myself or any of my co-authors. Thank you.